morning, Dr. Greaves.
How did you get on with the exercises in mass spectrometry that I set for you?
Okay, I managed to do them, but I had a few problems and I'm not sure that I understand it fully.
Can you tell me, what does a mass spectrometer actually do?
It generates the ions and then weighs them systematically.
Yes, in fact, it's a very useful technique because it's extremely sensitive, needing only very, very small amounts of material to get the mass spectrum. You can operate on 1 picogram, which is 10 to the minus 12 of a gram, which means you can look for biological pollutants in soil samples or for illegal stimulant drugs in samples taken from racehorses, for example. So it's really a very useful technique.
I know roughly how the mass spec works, but I'm not sure I understand it fully in detail how it really works. If you could explain it to me.
Yes, of course. In fact, I have a diagram here of a high-resolution mass spectrometer. And the first task is, of course, to get the sample into the machine, and this comes in at the source. And this entire apparatus is maintained at a very high vacuum, so that even quite large molecules become volatile at these pressures. And so you end up with the molecules of the sample in the gas phase. The first task is to convert them into ions for analysis. You mentioned the production of the ions, and we'll come on to that in more detail later on. Once the ion beam is formed in the source, it passes through these two slits, which just make sure it's a compact beam, and it's accelerated through a potential so that the ion beam is moving at some speed. It then enters this region of the mass spectrometer, known as the electrostatic analyzer. And here the beam is subject to an electrostatic field with the poles as shown, so that all the ions are exiting from this quadrant with the same velocity. Because if they're going too fast, they sail off into that wall, and if they're going too slowly, they end up being attracted to the negative plate. They then go through another slit before entering the magnetic analyzer. This is a sector where there's a powerful magnetic field, and the charged ions follow a circular trajectory in this analyzer, corresponding to their mass. Eventually they emerge at the other end, pass through another slit, and then into the collector, where the number of ions of a particular mass can be weighed. By scanning the magnetic field, it's possible therefore to scan the mass. And so you end up with a plot of mass over charge, m over z along the bottom, versus abundance along the top.
I see. Could you explain exactly how the magnetic analyzer works, please?
Yes, in fact I have a more detailed diagram of it here. It actually shows a full semicircular magnetic analyzer, such as was found on some of the earlier designs of mass spectrometer. You can see once again the ion beam from the source passes through a slit into this region of a high magnetic field. And from the equations of motion in a magnetic field, a charged particle follows a circular path. Now the radius of the path, r, shows the width of the circular path. And it comes from this equation where m over z, the mass over the charge, is equal to the square of the field, b in this case, times the square of the radius, all over twice the voltage. So, just as in the electrostatic analyzer, the magnetic analyzer discriminates between ions with the appropriate mass over charge ratio, which can go all the way through to the slit and then ultimately to be collected, whereas those that are either too heavy or too highly charged are not deflected enough and so don't make it, or are deflected too much and so hit the inside of the magnetic analyzer. And so this is what really separates the ions in a mass spectrometer.
You've explained how you collect one m over z value. Could you explain how you collect all the others?
Well, as you can see from this equation, by either varying the strength of the magnetic field, B, which is usually the case, or alternatively by varying the accelerating voltage, V, it's possible to allow any particular mass to charge ratio to emerge at the collector. So it's possible to scan the spectrum by varying either B or V.
Could you explain to me how you generate the ions?
Yes, this takes place in the ion chamber or source. What we have to do first is to introduce the sample, and that's done with a probe which actually places the sample in this high vacuum region somewhere near a heated filament. Now, from this heated filament, electrons are given out, and they're attracted to the anode here, and so shoot through the sample. Now, the potential difference here is usually about 70 volts. So they have an energy of 70 electron volts, which is a lot of energy. And as they pass through this cloud, they ionise the sample, making in fact positive ions. Now we have here a repeller plate, which is also maintained at a positive potential. And so these repel one another, and the newly formed positive ions are driven out through these two slits and into the rest of the mass spectrometer.
Could you explain why, from using neutral molecules, we get a positive ion when we bombard it with negative electrons?
The reason that you can get positive ions from bombardment by an electron beam is because these electrons have so much energy they can't be captured by the sample molecules to give negative ions. They would just fragment. But what happens is that they just knock an electron out of the shells around the sample molecules and so generate positive ions.
Are there any other methods of generating ions at all?
Yes, in fact, for samples that fragment very readily under electron impact ionisation, which is what I've just been talking about here, a new technique called chemical ionisation is particularly valuable. Here, instead of a beam of electrons, a beam of ions, often ammonia or methane, are used to bombard the sample, and this produces ions in a more gentle fashion, so you get less fragmentation, and the molecular ion, that of the parent molecule, is more visible. Another problem that's often encountered is samples that are either very polar or of very, very low volatility. Something like a peptide or a protein could fall into this category. And here you can't get the sample into the gas phase. So a technique known as fast atom bombardment, or FAB for short, has been developed, where the sample is put into a matrix of inert material and then bombarded by a fast stream of inert gas atoms, usually argon or xenon. And this knocks a molecule out of the matrix, which is then ionised and goes off into the spectrometer. And Fab mass spectrometry is a very powerful technique for polypeptide analysis based on actually sequencing the amino acids.
Do the ions ever break down at all between the source and the collector?
Yes, indeed, because once they've been energised with this large amount of energy from the bombarding electrons, there is the possibility for molecular fragmentation and indeed rearrangement. Now, if this happens once they're in the body of the spectrometer, then these ions come at an unusual place because they've actually changed mass in the course of the analysis, and these give rise to what are known as metastable peaks. These can be of value for actually detecting fragmentations from their accurate position, but modern mass spectrometers, which operate digitally, don't usually detect these metastable peaks, and so they're of less importance than was once the case.
Right, well, I think I understand it all now.
Good. Well, let's go and actually take a look at a mass spectrometer and see how all this fits together.
Okay.
Hello, Alan.
Hi, Nick.
I wonder if you could show Lisa the mass spectrometer.
Certainly, yes. This is a typical double focusing mass spectrometer.
How do we get the sample into the mass spectrometer?
Well, we've got a number of inlets on this system. We have here a solid probe inlet for analysing solids. The sample is put in a small tube on the end of the probe, and the probe is inserted into the lock, and which can then be pushed into the source, where it is warmed by the source and vaporized and the sample ionized. This is a septum inlet for gases and volatile liquids. We inject the sample using a syringe. We have two inlets for the gas chromatograph. One is for packed columns and one is for capillary columns. The gas chromatograph is used so that we can analyze mixtures using the mass spectrometer. The sample is injected into the gas chromatograph. The column separates the sample into its individual components, which one after another are fed through towards the source of the instrument. There they're ionized one at a time, and so we can get individual mass spectra of each component rather than a mass spectrum of the mixture. This is a very, very powerful technique. The way the sample is ionized is it is bombarded by electrons within the source region here. There are two main regions of the mass spectrometer. One is the source region, which is this part of the instrument here, and the other is the analyzer region. This focuses the kinetic energy of the ions because there's a small spread of kinetic energy inherent in the ion beam, and this would cause a blurred image at the collector end. So we focus the kinetic energy using the electrostatic analyzer. This bends the beam through this angle here towards the main part of the instrument, which is the magnetic analyzer. This consists of an electromagnet through which a current can be passed to change its magnetic field. For a particular ion, only one particular magnetic field will allow it to pass through this angle here and onto a collector slit which is beneath this control. So by varying the magnetic field, we can focus the ions one after another onto the collector slit. They travel through the slit and are bent towards a conversion dynode. This converts the ions into electrons, which are then fired across towards a detector, which is an electron multiplier. The electron multiplier has a gain of about 10 to the 6, therefore it amplifies the signal by a factor of about 1,000,000. The signal is then passed through a preamplifier and then onto the main control console of the instrument. I'll show you how we inject a liquid sample into the septum inlet here. I've got a sample here. We use a 1 microliter syringe, and I'll inject about a microliter. The sample now is in the reservoir here, and it is flowing through a fine capillary into the source region. There's enough sample here to last many hours, so we can get many spectra from it. We can now see a spectrum of the sample we've just injected on the screen. We can obtain a hard copy for reference, which will be plotted out on the plotter. There you are, Lisa.
Thank you very much.
Thank you very much. I think we've seen all we need to. Right, now that we've seen a mass spectrometer in action, let's have a look at some mass spectra. The first thing to notice with a mass spectrum is that we've got the M/Z scale along the x-axis, running from 0 on the left, and then the abundance scale, which is always fixed so that the maximum abundance is at 100%, just indicating the number of ions that were detected at the collector. And as you can see, you get a plot, a sort of bar graph, with each of these lines corresponding to the number of ions detected at each mass over charge ratio. And usually the first thing that you do with a mass spectrum is look for the peaks at the highest mass possible, because this is where you're most likely to find the ion corresponding to the molecular structure with just a single electron knocked out of it. And that's known as the M+ ion, or molecular ion. You then see fragment ions due to breakdown of the molecule corresponding to all these clusters of peaks here. Now, I don't want to concentrate on this particular fragmentation. This spectrum merely illustrates that at 159 units, which is the molecular mass of this aromatic compound, there is a sizable peak. The other thing to notice is that 159 is an odd number, and this is unusual in mass spectrometry. It shows that there's one nitrogen atom in the molecule. You'll see that all the other ones have even molecular ions, so that's an easy thing to look for. I mentioned earlier about a high-resolution mass spectrometer, and I'd like to explain now exactly what I mean by that. Running a traditional low-resolution machine, you don't get precise values for the masses corresponding to the peaks. When I say precise, I'm talking about to within 1 part in a million, so you have 4 or 5 decimal places. You usually only get integral values. But by using a high-resolution machine, such as the one we've just seen, it's possible to measure masses with much greater accuracy. So that, for example, if you look at an atom of carbon-12, its exact mass is 12 with a very large number of zeros after it. Whereas hydrogen actually weighs slightly more than 1. Correspondingly, oxygen slightly less than 16, and nitrogen just a little bit more than 14. Now, taking advantage of high resolution, it's possible to measure the ions observed with this sort of precision. And that enables you to distinguish between compounds that would otherwise give rise to ions in the same place. Now, I've picked out 3 examples here: nitrogen, ethene, and carbon monoxide. Now, they all have an integral mass of 28, so you might not know which one was which in the mass spectrum. But by using high resolution, it's possible to see that they are in fact significantly different. Carbon monoxide is less than 28, ethene, I beg your pardon, is greater, whereas nitrogen is the closest. And with that sort of analysis, it's possible to distinguish between particular molecular formulae for an unknown. One of the disadvantages of high resolution is that because you're cutting down the slit width in order to get the accuracy, you cut down on the sensitivity, and so you need more sample in order to get a good spectrum. Another feature that's immediately apparent in many mass spectra are the so-called isotope clusters. This is where, instead of getting just a single peak corresponding to an ion, you actually see a cluster of peaks around that value corresponding to slightly different compositions. Now, in the case of carbon, there's carbon-12, which is the most abundant isotope, but you also see 1.1% of carbon-13, and that means you usually see a small satellite peak on the right of the large peak. Now, if you look at the spectrum of this compound, each of these very large lines has a smaller line just to the right of it. And that's due to the molecules with 1 carbon-13 present in place of a carbon-12. The other striking feature of this spectrum is that you actually have a more complicated cluster than that, because we've got 2 very large lines of approximately equal intensity. Now, this is characteristic of a bromine being present in the molecule. 2 isotopes of bromine coming in at 79 and 81 mass units respectively, and this gives rise to a 1-to-1 ratio in approximately equal intensity. And this is perpetuated through the molecule wherever the bromine is present, such as you can see here between 117 and 119. The other halogen that shows a similar phenomenon is chlorine. This time the isotopes are 35 and 37, and they're in the ratio of 3-to-1 in favour of 35. And so I hope you can immediately see this molecular ion has a major peak and then a smaller one, about a third the intensity, and of course you always get the carbon-13 satellites as well. And so that structure immediately tells you that you've got a chlorine present in the molecule. And once again, the disappearance of this pattern shows the disappearance of the chlorine during the fragmentations. Now you can make this analysis more sophisticated, and I've gone to a schematic representation rather than real compounds for this. This is a repeat of one chlorine in the molecule, showing the ratio of 3 to 1 with a little carbon-13 satellite in between. This is for bromine, again 1 to 1, separated by 2 mass units with a little satellite in between. If you put 2 chlorines, then you end up with this pattern, decreasing but 3 large peaks, separated by 2 in each case. Whereas with 2 bromine atoms, you end up with a 1 to 2 to 1 ratio, corresponding to m plus 2, and m plus 4. And so whenever you see this sort of pattern, you immediately know that you've got a halogen in your molecule, and by more sophisticated analysis, it's possible to work out how many halogens and what sort they are.
You've talked about fragmentation. Can you explain some more about it for me, please?
I've got a spectrum here of a simple hydrocarbon, octane. And the first thing to notice is the molecular ion present at 114. An even number because there are no nitrogens in this molecule. And then you'll notice a sort of increasing curve of peaks separated by 14 mass units. So 85 to 71 is 14, 71 to 57 is 14, 57 to 43 is 14. And each of those clusters corresponds to this alkyl chain with increasing numbers of units removed. So fragmentation is occurring at the carbon-carbon bonds in turn, giving rise to each of these isotope clusters. That's a very simple molecule. If we move on to slightly more complicated ether, you again see a molecular ion at 130 mass units. And ethers can cleave in one of 2 ways commonly. They can either cleave at the bond alpha to the heteroatom, alpha to the oxygen, in which case that's a loss of, it takes it down to 87. Or alternatively, it can cleave actually the carbon heteroatom bond, in which case the butyl group is lost, and that gives rise to the peak at 57. So that's an ether. Another very common type of molecule is an alcohol. And here's 3-hexanol. Has a molecular ion, very, very small molecular ion. And as is frequent with alcohols, there's a loss of water. That's a loss of H2O, 18, and that takes us down to 84. Alcohols, rather like ethers, typically cleave the alpha bonds, either that one or that one, giving rise to these 2 fragments, the 59 and 73 respectively. So now you've had a bit of an introduction to mass spectra and their interpretation and looking at the fragmentation patterns. Would you like to have a go at some spectra? There's one to start with.
On this spectrum we can see there's a very weak molecular ion peak here. There is bromine present because we've got this 1-to-1 ratio with 2 mass units separating them. And here we have a loss of an ethyl group. Still bromine present because of the isotope ratios. Here though we can see the ion is only a single, there's no isotope effect, which would correspond to the loss of the bromine here, and then further alkane fragmentation.
Good. Let's have a look at this ketone.
Well, we've got the molecular iron at 114, then an iron peak at 85, which corresponds to cleavage here. And we've got a peak at 57, which corresponds to cleavage here, with both halves being equal to 57. What I'm not very sure on is why we've got a peak at 72, because it's an even peak, and you'd expect it to be an odd peak.
Yes, that's due to a rearrangement occurring rather than a fragmentation. All the fragment peaks we've seen so far give rise to odd masses, but rearrangements can give rise to even. And this particular rearrangement, known as the McLafferty rearrangement, is characteristic of compounds containing a carbonyl group, with a hydrogen at the gamma carbon. So numbering from the carbonyl, alpha, beta, gamma, this hydrogen sits in a six-membered ring with respect to the oxygen. And so there's a nice, stable cyclic transition state for the hydrogen to hop across onto the oxygen, and with corresponding bond reorganisation, we end up with these two fragments. This enol fragment is the one that gives rise to the rearrangement peak at 72. So you can see 114 for the molecular iron gives rise to the even peak at 72 after the McLafferty rearrangement.
I see.
Now here is an aromatic compound.
Well, we have the molecular iron here at 106, and then we have cleavage here to give the peak at 91, which is C7H7+. Then we have cleavage here to give the peak at 77, which is C6H5+. And then the peaks from here onwards are just a breakdown of the aromatic ring.
Good. Now here's another important functional group, an ester.
Well, we've got a very small peak here, which I think is the molecular iron peak. And that's at 116. And because it's an ester, you can get cleavage here, which would generate the methyl. So we get characteristic loss of a methyl, and then the peak here at 101. We also get cleavage of this bond here, which generates methoxy, and then this iron left here, which is the peak at 85. And we've also got the even peak at 74, which is characteristic of the McLafferty rearrangement.
Yes, well spotted. And as you can see, the McLafferty rearrangement occurs whenever there's a carbonyl with a gamma hydrogen, and can give rise to peaks which have really very large intensity, as in this case. So I hope what we've seen today, looking at mass spectrometry, is that the first thing is to operate with a high resolution machine, so that you'll get accurate values for the ions, which in turn enables you to calculate precise atomic composition. The next thing to do is to look and find your molecular ion, if there is one, which means looking at the far right of the spectrum. And if that ion is even, you can immediately eliminate an odd number of nitrogens from your calculations, whereas if it's an odd peak for the molecular ion, you know that there are an odd number of nitrogens, so there's an immediate clue. The other thing to look for is, of course, the isotope cluster patterns that we saw earlier, corresponding to the halogens, and they can give very useful information about their presence in a given structure. You then need to look at the fragmentations, looking at simple loss of functional groups, sometimes loss of the halogen with the corresponding change in the isotope patterns, and then lastly you have to watch out for rearrangements which give rise to even peaks, such as the McLafferty rearrangement that we've seen here.
Thanks very much for all your help, Dr. Greaves.
It's a pleasure.